Hello everybody. So today we are going to talk about partial differential equations. And actually we will see that this topic, which is a mathematical topic, has nothing to do directly with finance. However, it is linked to finance. Because one type of a partial differential equation is closely linked to the so-called Black-Scholes model we are going to study in one of the next classes. And before we are able to study and to solve the Black-Scholes model, we have to learn and see a little bit what is a partial differential equation, how can we solve a partial differential equation, and that is what we are going to do to talk about today. So this is a completely new topic, and you will see at some point it's also a difficult topic for you, but as you will also see during this class, there is a nice relationship between the finance and the Black-Scholes model and partial differential equations, and also other issues we already have talked about. Brownian motions are linked to partial differential equations. Probability density functions are linked to Brownian motions, and they are linked to partial differential equations. And stochastic differential equations, which capture and model a Brownian motion, is also linked to partial differential equation. Actually, there is a close linkage which goes very deep into mathematical theory, the so-called Feynman-Cox theorem, and we will later on see at the end a little bit of this. So let me start first with the topic of the day, an introduction to what we call partial differential equations. So the first block is I will tell you a little bit about the terminology and how different types of partial differential equation looks like, right? So I give you some terminology at the beginning, and then we move on to solving these, or a special type. That is what we will see. So the first, let me say, first is terminology. By the way, for this term, partial differential equations, usually in books, because you know these are 3 words and very long, we use a short, PDE. So this is a short for partial differential equations. So what is a partial differential equations? How can you imagine how this looks like in general? Well, let me start with the definition. So a partial differential equation is a special function. It's a function that is dependent on the function itself and the derivatives. However, due to the fact that here we have a function dependent on more than one variable, we call it a partial differential equation. Differential equation means there are derivatives and the function. And partial because we have partial derivatives. So definition, a PDE, a partial differential equation, is a function, let's say, of the form, and now I write it like f, and this function is dependent on variables. Let's say there is an x1 variable and there is an x2 variable. Yeah, then we can stop and say that's a function of 2 variables, and if we calculate the derivatives, we have partial derivatives. Well, if I do this in more general, then we have not only 2 variables, let's say we have n variables. Yeah? And we have not only, if we talk about a PDE, n variables, we also have the derivative of these n variables in this function. So you can say we have inside the function u with the first derivatives, and of the second derivative x2 until the xn. That are the first derivative. And actually we can generalize and say, well, maybe we have even second order derivatives in it. So u in respect of 2 times x1, yeah, until uxn. And so on. You can also include third derivatives until n derivatives. So I will stop here. So it's a very general function with more than two variables, and it includes also the derivatives. Well, this is very cryptic in a sense, and now I will give you some examples. Before I will give you an example, let me categorize PDEs in more general. So if we look to so-called partial differential equations, we distinguish usually between linear partial differential equations and nonlinear. So we distinguish in general between so-called linear PDEs and on the other side so-called non-linear PDEs. Most of my class today, you are lucky, is just about linear PDEs. Well, if we are closer to research and closer to reality, what is going on? Obviously, we know that many of the phenomena in the stock market, but also in nature, are not linear, they are nonlinear. But we are concentrating on linear. Regarding nonlinear, however, we also distinguish certain types. There are different types of nonlinear, and I will just at least name you and tell you these types without going into the details. Well, we distinguish here between so-called semi-linear, nonlinear types. We also have so-called quasi-linear, nonlinear PDEs, and we have full nonlinear PDEs. Full nonlinear PDEs. So there are certain subtypes of semi and quasi-linear type of nonlinears. And well, semi-linear, nonlinear PDEs are just nonlinear in these variables, and they are linear in the derivatives. That is what we will call a semi-linear. A quasi-linear is the opposite. So a quasi-linear is maybe linear here in the variables, but it is non-linear in the highest derivative terms. That is what we call in theory quasi-linear. Well, anyway, we will not talk about nonlinear, but just to give you, if you read a book and you wonder why they call some equations semi or quasi-linear, that are special nonlinear types. So now let me talk about examples. I think that makes the point a little bit clearer regarding this definition of a PDE and how does this look in more explicit terms. So let me give you some examples. The first example of a linear partial differential equation I will describe here, let's call it number one, is the so-called transport equation. Or PDE, in general. The transport equation is modeling the following fact. Suppose you have a substance in a river, and then you follow how this substance in the river is moving over time and space. So where is this substance, the next time period, at what space? And the transport equation is actually telling us the dynamics of this substance. And how can we describe this in mathematics? Well, it can be described by a partial differential equation. And this partial differential equation looks like there is a derivative of a function u in respect of t plus v, which you can say is the speed of the substance moving this river, because you know the water has a certain speed in this river, and that is this velocity, you can say, times u, and x is the first partial derivative of this function u in respect of x. X is the space variable, right? And t is the time variable, equals to 0. This equation is this is a partial differential equation. It's a first order differential equation. Why? Because I have, in general, you can say I have a function dependent on x and t. The function depends on two variables. X is space, t is time. And now I have the time derivative in this equation and the space derivative in this equation. Yeah, it's a function of two variables, at least. Yeah? And we have the derivatives, and they are in the same line. And therefore we call this a first order, because we have first derivative, partial differential equation. And v, once again, is the velocity. And the question at all these, at the whole day is, well, what function u of x and t is satisfying this equation? Yeah? So we have to find the corresponding function u of x and t that satisfies this condition. That the time derivative of the function times v plus the space derivative is equal to 0. This is the first example of a PDE, a partial differential equation. So let me give you a second example. The second example is, and that is the most important for us, in particular because this has a deep relationship to finance, and I will concentrate mainly today on focusing on this type of equation. And we are not talking about transport equation and other types. So the second is what we call the heat equation. The heat, or sometimes it is called the diffusion equation. This is also a partial differential equation, the heat equation. And it looks like this. So we have the time derivative, u subscript t. It's a partial derivative of my function u in respect of time. Then we have minus a certain constant, call this d, yeah, times the space derivative. However, the space derivative, it's the second derivative, equals 0. This equation, first derivative in respect of time, minus some constant d times the second derivative in respect of space. So whenever you have an equation that looks like this, we call it a heat equation. What does a heat equation is modeling? Well, it comes from physics, as transport and the name heat equation already implies. Suppose you have a heat source in this room, a heating, like here on the side, or this heating is underwater. And now what you are interested in, how does the heat develops and spreads in this room? Yeah? How long does it take that the heat comes here, and so what is the temperature then at that point, or at that point, or at that point? So this equation, you know, this heat is evolving and is mixing with the other air, and we want to study and learn how does the heat is interacting with the existing air in this room, or if we have the heat source in a box of water, let's say, yeah, how does this is warming up my water? And that is modeled by this type of heat equation. So the d is a kind of constant that has to do with the material, right? Whether we have the heat source, let's say here in a room, or underwater, or in a other substance like oil or something like that. And once again, we have a function u dependent on x and t, yeah? And we are looking for u that the first derivative of time and the second derivative of space satisfy this equation. So we have to find a function u of these two variables that is in line with this equation. And as I already said, the heat equation is actually very close to finance. In the end, what we can do when we will talk in the next weeks about the Black-Scholes model, which price a financial derivative, a call or a put option. This Black-Scholes equation turns out to be also a second order partial differential equation. And luckily, this is far more complex than Black-Scholes equation. However, luckily, we can simplify this equation, the Black-Scholes equation, into an equation of this type, of the heat equation. And due to the fact that we will learn today how to solve the heat equation, we can first take the Black-Scholes equation, simplify it to a heat equation, then we know the solution of the heat equation, what we will discuss today, and then we do the retransform into the Black-Scholes model of the variables, and then we have obviously the solution of the Black-Scholes model. And therefore the heat equation is of special interest today in this class, and it is of special interest in finance. Let me give a third type of example, and all these examples so far are linear partial differential equations. Another interesting partial differential equation, which we will not discuss in detail, just I will give you the example here, is the so-called wave equation. Well, the wave equation, as you can already imagine from the name, is modeling the wave behavior. Suppose you are looking to the sea, right? And you see these waves, some are big and some are crater, and you see the wave is moving over time and space. Yeah? And the wave equation is actually the corresponding mathematical model to describe moving waves. And this looks like there is a second derivative in respect of time plus a certain let's call it also v, velocity, yeah, the movement, the speed of the wave, times the second derivative in respect of the space of the function equals 0. So second derivative in respect of time of my function u and second derivative in respect of space is modeling a moving wave. Now you may wonder, why? Well, actually, and that is what I will not do because we are not a physics class, you can really derive by reasoning about waves and by thinking about how can you describe a wave from a very basic physical description that you will end up with this. You can derive that a wave is described by this equation. You can derive that a particle transported in a river is described by this equation. So this is not just given because I know this. You can really derive these equations, and you will see, starting from, well, you suppose there is a particle at point x and t, and then you think about how does this particle moves up over time, and you will see that this can be modeled. Then in the end it turns out that this is the equation that models this behavior. I will not derive this. This is due to time. I have not the time to do this. But believe me, you can really show that all these equations I told you so far are really popping up due to reasoning. How does a wave move? Wave equation. How does a heat source spread into a room, or how does a particle transports in a river? Can be described by these equations. Well, there's a fourth type of equation which I have to talk about a little bit here. Let me squeeze it in here. 4. Because it is linked somehow to my heat equation. And this is what we will call the Laplace equation. Laplace equation. So what is the Laplace equation about? Well, in the Laplace equation we assume that the variable or the function u does not change over time. That means u of t, which is the change of the function over time, yeah, this u of t, this derivative, is assumed to be 0. And if this is 0, right, and if we assume the d for a second is 1, you see immediately you get a term that the second derivative of my space variable is 0, right? If you assume this is 1, the minus does not care because of the other side is 0. You see immediately you get something like this. Second time derivative is equal to 0. And this is what we call the Laplace equation. And now I come back to what we have already learned in macroeconomics. In macroeconomics, at one point, maybe some of you remember, we assumed that there is no change of my variable over time. Can you remember? what was this? In steady state. That was a description and the definition of a steady state. In steady state, the variable does not change over time. And therefore, you can say the Laplace equation describes a steady state at point. Yeah? This is a description of a steady state, or you can say also in sloppy words, an equilibrium. And therefore, the Laplace equation has also special importance and meaning in finance, in economics in special, but also in mathematics, obviously. There are some other interesting points. So from this assumption, in the case of the Laplace equation, you see that uxx is 0. But this is only because I assume that my heat equation or my transport equation, they are always equal to 0, right? And when this is the case, when we have 0 on the right-hand side, we call this is a homogeneous partial differential equation. But in more general terms, it can also be a certain value. Let's call it f. Or a function can be even on the right-hand side. Whenever there is not 0 on the right-hand side, we call it an inhomogeneous partial differential equation. So if there is 0, we call it a homogeneous. Yeah? This is a homogeneous partial differential equation. And whenever we have a fixed value here on the right-hand side, we call it an homogeneous partial differential equation. And it's all about terminology, you see. We are not doing any calculus so far. And now let me come back to my Laplace example, because the Laplace example, right, we have 0 here. When we plug, however, here a value in, it's not equal to 0, it's equal to some value f, let's say, then this Laplace equation has a new name. It's not called here inhomogeneous Laplace equation. It's called then a so-called Poisson equation. And you are all familiar somehow with this name, because I know that in statistics you already have talked about the Poisson distribution. Yeah? And that comes from, you can say, such a second order differential equation. Okay, so what we have seen here now in the first introductory part is that a PDE, a partial differential equation, is a function, in general, of at least 2 or more variables, and it contains not only these 2 or more variables, there are also these derivatives of this function in this equation, right? Derivative in respect of t, second derivative in respect of x. And what I'm going to do today is I will concentrate exclusively on solving the heat equation or diffusion equation, because this is closely linked to the Black-Scholes model. We are not studying here how to solve a transport equation, how to solve a wave equation, how to solve other types of equations. We are concentrating on this. And you will see that's already quite hard to do, and every type has different ways to solution. There is no common solution procedure, as you hope, or as you may think about what you have learned in mathematics so far. Here we are in a field where every equation has different methods how to solve these, and sometimes even not only for the same type of equation, you cannot apply for all types this method. Sometimes you have different heat equations depending on what is D here or what is F here, then you have to find a new method how to solve, because the one method just works for a certain type of heat equation. So it's quite complex to do. A final word to nonlinear. I have talked about examples. Can I give you just some examples of nonlinear partial differential equations? For instance, Schrödinger's equation, which is an equation that is modeling behavior in quantum physics. Or Maxwell's equation is also a nonlinear PDE. It's modeling electrodynamics. or the Navier-Stokes equation, which is also a phenomena which we have in physics, which is also here a nonlinear PDE. By the way, the Navier-Stokes equation, there's still an unsolved problem, and if you can solve this, you will get 1 million. Yeah, so it's you have just to solve the nonlinear Navier-Stokes equation for a special parameter z. You can get 1 million. It's quite easy to do, if you like. Okay, so that's about the first part of terminology. In my second part, I will give you a kind of how is a partial differential equation related to other phenomena we already have talked about.